Okay, welcome. My name is Martin O'Hara. We're at Immaculate Conception in Center Harbor, New Hampshire on a nice cold morning. This is our pre-calculus class. Today we're going to be discovering the explicit formulas for sum of consecutive integers, sum of consecutive squares, sum of consecutive cubes. You get the idea. Okay. We need the consecutive sums for the calculus. Consecutive sums are used for simple integrals in calculus. Remember, the integral and the derivative are the two kinds of limits that we're going to be studying in calculus. The integral is the equivalent of our area functions, right? That we worked with Archimedes on the graph. We found an area function underneath the curve, and that area function will be replaced with an integral in calculus. But to do the simple integrals, we need to discover the explicit formulas for what? Sum of consecutive integers, sum of consecutive squares, sum of consecutive. Now, last class we did some work with successive differences. We said, okay, we saw that if we have an explicit formula of a first degree explicit formula generating a series, right? One difference produces a constant difference, right? If I have an explicit formula generating a what? A second degree explicit formula generating a series, then two successive differences produced a constant. And then we did a third example. We said if I have a third degree explicit formula, right? And it takes what? Three successive differences to produce a constant. And from that experience, we came up with the general principle. What was the general principle? And I'll say it first. You pay attention because I'm going to have to repeat it. Okay? So the general principle was that the degree of the explicit formula equals the number of successive differences necessary to produce a constant. The degree of the explicit formula equals the number of successive differences required to produce a constant. Now let's hear that in one melodious voice. Hear it.
The degree of successive differences.
No. The degree of the explicit formula equals, pay attention, I'm going to hold this. The degree of the explicit formula equals the number of successive differences required to produce a constant. Let's try it again.
The degree of explicit formulas equals the number of successive differences required to produce a constant.
There you go. Again, try it again. The degree
of the explicit formula equals the number of successive differences required to produce a constant.
All right, so enough talk. Let's just do an example on the board. There's nothing like an example. What I have here is a series that you've never seen before. But everybody make sure you have your calculators out and ready. I'm not going to be wasting time. So I'm going to put a series on the board. And what we're going to do is figure out its explicit formula. So, first term A1 is going to be -4. A2 is going to be 1.25. A3 is going to be 11. And A4 is going to be 25.25. And A5 is going to be 44. A6 is going to be, that's not good, 67.25. And then it just keeps going. So this is a series of numbers. -4, 1.25, 11, 25.5, 44, 67.25. Okay? Now I'm going to ask you, what's the 10th term in that series? What's A10? Everybody just take a good look at that puppy. What's A10 equal to? Anybody have any clue? I'd be very surprised if you did. You're not going to find it. But if you know the explicit formula for this series, right, then I can ask you any what term, and you'll be able to discover what that value is. But the successive difference principle, the degree of the explicit formula equals the number of differences that it requires to get a constant. We're going to use that successive difference principle to discover the explicit formula for this system. So, and so on. We're going to take a difference here. What's 1.25 minus negative 4?
5.25.
How much is it?
5.25.
Do I have concurrence?
Yes.
All right, how much is it? How about a marker that works? How much is it?
5.25.
All right. Anthony, 11 minus 1.25.
9.75.
Oh, 9.75. Do I have a constant difference?
No.
No, so we keep going. Anthony, 9.75 minus 5.25.
4.5.
How much?
4.5.
4.5. Okay, we just have to build that. Okay, David, 25.25 minus 11.
14.25.
14.25, right? Minus what? 9, I'm going to fall off here. Minus 9.75.
4.5.
4.5. Oh my gosh, look at that. And just to confirm this, right? Let's do one more. We got, oh, Joseph, 44 minus this mess.
18.75.
18.75 minus 14.25. 4.5. So what do we have here? Did one difference produce a constant? No. But two differences did produce a constant, didn't it? What does this tell us about our series?
Second degree.
It has a second degree explicit formula. Right? So the explicit formula for this series is of degree 2. Which means that AN, I'll just put it in general up here, AN is going to look like what? Well, I don't know what the coefficients are, but they're going to be AN squared, that makes it a second degree, right? Plus N, plus what?
BN.
Plus BN, thank you, okay. Plus BN plus C. The explicit formula for our series here is going to look like that. But you say, we still don't know what the explicit formula is, do we? Because we don't know what little a, little b, little c are. So what we have to do is reason together to discover what a, b, and c are. And when we reason, we advance from things that we know to investigate the things that we don't know. Now, what do we know? What do we know? We know that A1 is what? Negative 4. We know that A2 is?
1.25.
And A3 is?
11.
So when N is 1, right? A1 is?
Negative 4.
And so we're going to use that bit of information to make this more concrete. Right? So A1, so when N is 1, we get what? Well, A times 1 squared, right? Plus B times 1 plus C. Clear? Okay? Of course, this can be simplified. I'm going to simplify it down here, so little white space management skills. Okay? So we get what? That has to be equal to A1. It's going to be equal to negative 4. So this becomes just what? Class A plus B plus C equals negative 4.
A squared.
We're getting a squared.
Oh.
Who's getting a squared? Oh, no. No, okay. It's not a squared, it's 1 squared. 1 squared is what? 1, okay. Okay, so now what? We look at what we have. I've got an equation with 3 unknowns. Are we going to get a unique solution for an equation with 1 equation with 3 unknowns? No. How many equations do I need?
3.
I need 3 equations to get a unique solution for 3 unknowns, don't I? So where do I get my second equation?
A2.
Well, look at A2. We know that A2, again, we go from what we know, A2 is equal to 1.25, isn't it? And what value is n for 1.25? So 2, right? So what do? Well, I'm not going to do this middle step. We can do this in our heads. Right? So if we get what? N is equal to 2. So we get 2 squared is?
4.
4 what? 4a. 4a plus, well, when n is equal to 2, we get what? 2b. 2b and plus c. And that sum has to be equal to a2. What's a2?
1.25.
1 point how much?
25.
1.25. Now I've got a system of 2 equations with 3 unknowns. Is that going to give me a unique solution? No, we need what? We need 1 more. So we do what?
A3.
A3 is 11, right? And so when n is equal to 3, we get what? Quickly, class, pick up the pace.
9a plus 20b plus c equals to 11.
Equals to 11. Now, at this point, we say I've got a system of 3 equations with 3 unknowns. Now we can either go through all the what? Substitutions and eliminations that we did in advanced algebra, whatever. Or we can use what we know about matrices and let the black box do the work for us. Now, which one do you want to do?
Black box.
All right, so we can break this thing up into a coefficient matrix. What's the coefficient matrix, class, together, please? In one voice.
1, 1, 1, 4, 2, 1, 9, 3, 1.
And times a what? Times a what? The variable matrix. And what's the variable matrix?
A, B, C.
And we're going to get a what? A solution matrix, right? The solution matrix is going to be?
Negative 4, 1.25, 11.
An 11. Okay? So this is your coefficient matrix. This is your coefficient matrix times the what? Variable matrix V is equal to the solution matrix S. Now, don't let me down, but the issue is what? What did we prove about the variable matrix V? What do we know about the variable matrix V? Okay, in one voice. Okay. The variable matrix equals the inverse of the coefficient matrix times the solution matrix. Again, the variable matrix equals the inverse of the coefficient matrix times the solution matrix. So this V matrix is going to be equal to C inverse times what? S. Times S. Right? So now we take out the black box. Everybody, take out the little black box here, little calculator. See here. And hopefully it works. So, go into matrix, second matrix. We're going to edit what? Second matrix. Where's my matrix button? There we go. Edit. We're going to edit our coefficient matrix. So everybody hit C for your coefficient matrix. What's the dimension? Well, it looks like we got it here. It's what? So we'll do a 3 by 3, right? Okay, position 1, 1 is 1. So just pump them in. 1, 1, 1, 2 is what, class? 1, 3 is 2, 1,
4,
2, 2,
2,
2, 3.
1.
Oops, that's not a 1. And 3, 1,
9,
3, 2,
3,
and 3, 3.
1.
Okay, exit out of that. Hit alpha what? And you know, that better work. Make sure you have the right matrix in there. The other matrix you need is? Solution matrix, right? So we go back in, matrix, edit. We're going to call this S. Now S is what? It's 6, right? There's S, right? Now how big is the solution matrix?
3 by 1.
So we do 3, 1, 3 by 1, right? Okay, position 1 is what? Negation of 4, right? Then 1.25 and what?
11.
And 11. Okay, exit out of it. Hit what? S, and there's your what? Solution matrix. Now we just let the calculator do the work. We want to know what the variable matrix is, right? So the variable matrix is going to be what? So we hit alpha, C inverse, right? Times the what? Solution matrix, which is, right? Everybody see that? And look, what do we get? What do we get? So your solution matrix is what? Together I can't see it. So what's your solution matrix?
2.25.
It's 2.25.
Negative 1.5.
Negative 1.5.
Negative 4.75.
Negative 4.75. Okay, what good is that? Well, that's equal to A, B, and C, isn't it? Okay? So now we know what A, B, and C is. So, A, B, and C, that's right here. This is our explicit formula. Let's not lose track of what we're doing, right? The explicit formula becomes, class together, AN is equal to what? 2.25 is really what? How many quarters? 2 It's 2 1/4, which is how much? It's 5 halves, right? So it's 5 halves, so it's going to be what? Oh, no, not 5 halves. 9 halves. Don't listen to that guy. It's not 5 halves, it's 9 halves. So it's not even halves, it's 9 quarters. Right? What do we think? It's 9 quarters. 9 quarters what? N squared. Right?
Plus.
Not plus.
Minus.
Minus. How many halves is time?
3
This is minus 3 halves what? N. Minus
19.
Okay, this is going to be what? How many quarters? 16 plus 3 is what? Minus 19 over 4. It's not a particularly pretty explicit formula, is it? Well, let's see if it works. So let's just to see if it works, we'll do one of them that we know first. A5, right? So everybody get the calculator ready. So we have what? A5 is going to be equal to 9/4 times what? 5 squared, which is how much? 25. Minus 3 halves times what? 25. Minus 19. Oh, not 25. 5. Thank you. Times 5. Minus 19/4. What do you get, guys?
44.
Oh my goodness, the miracle of miracles, right? This is equal to 44. Okay? So your explicit formula worked for the known value. The fifth value is what? 44. So my question to you was, what's A10? Right? A10 is going to be equal to what? 9 9 over 4 times what? Times 100, right? Minus 3 over 2 times 10, right? Minus 19 over 4. And what's that equal to? 205 and a quarter. Do you see this? So, what have we done here? I gave you a random series of numbers, A1 through A6. We used successive differences to discover that it took 2 successive differences to get a constant. So we discovered that the explicit formula had to be of a second degree. And so it's going to look like that, but this explicit formula has A, B, and C. So we used what we knew about our first 3 terms in our series to discover a system of 3 equations with A, B, and C. Right? Then we used what we know about matrices, and we let the black box, right, solve for A, B, and C. Once we knew A, B, and C, then we plug that into our general form, and this becomes the explicit formula for the unknown series. Okay? See how this works? Okay, we good with this? Right? Now, our job is to discover the explicit formulas for the sum of consecutive integers, the sum of consecutive squares, the sum of consecutive cubes, and so on and so forth. Okay? That's our job. What we're going to do today is we're going to discover the sum of consecutive squares. As I pointed out in the last class, our little friend Blaise Pascal, right? Remember Blaise Pascal? The bright fellow, Pascal's triangle, do a lot of math, right? He discovered, as a youngster, the explicit formula for the sum of consecutive integers, right? The teacher said, I got to keep these guys busy. Okay, I want you to add the first 100 numbers, right? And I'm not going to go through that again. But he came up with what explicit formula? You guys remember? So the sum of the first n integers. Let's erase this. Clear it out. A gentleman and a scholar. Man. So we want to find, Pascal, he was told to find the sum of the first, 100 integers. He went back to his little desk and figured out, 5,050. But the formula that he came up with, and we're not going to go through that one because we already know this one. The sum of Sn equal to 1 plus 2 plus 3 plus ... n. The sum of the first n integers is equal to what? N squared over 2 plus n over 2. And that was, we saw how Pascal came up with that little thing. It's kind of brilliant. So, but today, Mr. O'Hare is going to ask you guys, what's the sum of the first 100 squares? Huh? So what is what? Sn equal to 1 squared plus 2 squared plus ... n squared. Well, actually, we'll do just the first 100. So we'll say S100 equal to 1 squared plus 2 squared plus ... 100 squared. Now, if you're going to do that, you can do it. Either little calculator, you do what? 1 squared plus 2 squared plus 3 squared plus... And when you're done with that, what do you have? Okay, so the sum of consecutive, what you'd have is the sum of the first 100 squares. But that would all you have. Okay? If we derive the explicit formula, then we can find the sum of any what? Number of squares. And that's what we're going to do. Okay? Let's just get down to business. In order to derive that explicit formula, we need to know what these terms are. S1, S2, S3, S4, S5, S6. You get the idea? S7. We have to find out what the first 7 sums are. So what's the first square? Where did I leave off? 1 squared. You got a tough one, didn't you? So this is equal to 1 squared. And 1 squared is equal to how much?
1.
All right. All right, there we go. Now, the sum of the first 2 squares, Luke, is going to be what? Well, it's going to be 1 squared plus 2 squared, and that's equal to 1 plus 4, which is 5, right, Luke? Now, but let's stay with Luke. The easy way, what's the easy way to figure out the sum of the first 3 squares? Well, we'll just do it. Maybe you'll see it. The easy way, we say 1 squared plus 2 squared plus 3 squared. Well, really, isn't that 1 squared plus 2 squared, right? Which is how much? 5 plus what?
9.
Plus 9, right? Right? So that's going to be, of course, how much? 14, right? So what's the easy way to figure out S4? 14 plus 4 squared, right? So you're just doing the previous, you already did all the work, right? So this is going to be what? 14 plus what? 4 squared is how much?
16.
Francois is going to be how much? 30. Felipe is going to be how much?
30 plus 5 squared?
30 plus 5 squared, what's 5 squared?
25.
This is 40, it's 25, right? So S4 was equal to 30, S5 was equal to, class, 55, S6 is equal to
91.
and S7 is equal to
140.
So what we have here is a series of numbers by looking at your partial sums here. Over here we'll draw out that series. S1 was what, class?
1.
S2?
5.
S3?
14.
S4?
30.
S5?
55.
S6?
91.
And S7.
140.
Okay, now let's get the calculators going. I know some of this won't take much, but where did I leave off? Ansel. This is easy. What do we get? 4. Okay, and just keep me going here. Ansel?
9.
9 and what? 5. So clearly we don't have a constant difference yet, do we? Anthony, I need concurrence. Everybody double check everybody's work. We need what? Anthony, we get what?
16.
Then what?
7.
Then what?
2.
2. Still no what? No constant difference. Okay? David, what do we get?
25.
25. Concurrence?
Yeah.
Then we get what?
9.
9.
And 2.
Ah, it's 2. Look at that. And just to confirm, Joseph, we get what?
36.
36.
11.
11. 2. So it seems to be that after 1, 2, 3 differences, we produced a constant. Right? After 3 differences, we produced a constant. What does this tell us? That the explicit, and let's use the grammar, the explicit formula is a 3rd degree equation. Right? So this has a 3rd degree explicit formula. And so it's going to look like what? Well, Sn is going to look like, class together. Well, it's going to be, I'm going to need a whole bunch. Yeah, okay, we'll do this. So we're going to this is a 3rd degree, so An what? Q plus Bn squared plus Cn plus D, right? Okay? Which means I'm going to need, this will end up a system of 4 equations, won't it? Okay? So the first equation, let's do this quickly. We're going to leave off. Okay, K-word. Our first equation, let n be equal to 1, right? We get what?
8.
Just, 1 times a, 1 to the 3rd is going to be just a plus what? B plus C plus D, and that has to be equal to what? It has to be equal, you got it easy. So S1 is 1, and the first term is 1. Okay, so that worked out pretty nice. Okay, Luke, the next one's going to be what?
8 times.
8 times 2 to the what? cubed? Let's say, what's 2 cubed?
8.
So we get what?
8A.
8a, and then 2 squared is how much?
4.
You get what? Plus 4b, and
2C
2c
plus B.
plus d, and that has to be our second term in the series. That has to be equal to 5. Okay, and Francis. Now we're going to what? Let n be equal to 3. When n is equal to 3, we have 14. Well, what's n cubed?
27.
So we get 27. 27a plus what?
9B.
9b plus
3C
3c plus
D.
d is equal to
14.
14. Okay, and Felipe, what do we get?
64A
64, we have concurrence with that? Plus what?
plus 16B
16b.
plus 4N
How about 4c? Where did that come from?
4C
4c
and plus D.
plus d, and that has to be equal to what, Felipe?
30.
Has to be equal to 30. Okay, so you guys are going to use the black box. So let's break this up as quickly as possible. You get a system, a matrix. Your coefficient matrix is what dimensions?
4 by 4 by 5.
It's a 4 by 4, isn't it? So this is going to be 1, 1, 1, 1, 8, 4, 2, 1, 27, what? 9, 3, 1, 64, 16, 4, 1. Your variable matrix in this case is A, B, C, D. And your solution matrix is 1, 5, 14, and 30. Okay? So I can erase this section right here, right? Right. So, class together, we know that the variable matrix class is equal to what?
The inverse of the coefficient.
The inverse of the coefficient matrix times the solution matrix. And so what do we get for our variable matrix? Class? 1/3? Really? Okay. So we get what?
1/3.
1/3, 1/2, 1/6,
0.
and 0. There's your what? Everybody? Did I get everybody on that? Anthony, did you get the same answer? Everybody get the same answer? Okay, good. And so that means A, B, C, D. That gives us the values for A, B, C, and D. So, our explicit formula, the sum of consecutive squares, becomes what, class? Everyone together? 1/3 n cubed plus 1/2 what? N squared. 1/6 n, and then plus 0. This is typically stated what? N cubed over 3 plus n squared over 2 plus n over 6. Now, what we want to do very quickly, let's confirm it with, say, n7. Class, n7 or s7? s7 is going to be equal to 7 cubed over 3 plus 7 squared over 2 plus 7 over 6. Get the calculators going.
343.
What do we get?
343. 343. 7 cubed.
No, I have to do the whole thing. One gets the whole answer.
144.
What do we get?
140.
This is equal to 140, isn't it? And 140, we look over here. 140 is in fact what we came up with what? The sum of the first 7 squares. Now my original question for you, of course, was what's the sum of the first 100 squares? Right? So your sum of the first 100 squares are going to be what class together?
100 cubed
100 cubed over
3
plus what?
100 squared
100 squared over 2 plus what?
100 over 6.
100 over 6. So let's get those things into the calculator. What do we get? Everybody?
33,000.
Okay, so what? Give me an answer here. 3.
8. 3.
Do I have concurrence? Everybody agree? Okay, so what have we done here? Okay, we started with a series of numbers representing the sum of the first 2, the first 3, the first 4, the first 5, the first 6, the first 7 squares. We set up that series, we did consecutive differences, we saw that 3 consecutive differences produced a constant. By the principle, we know that therefore the explicit formula has to be a third degree. We used our knowledge of the series to figure out a system of 4 equations. We used our knowledge of matrices to figure out the solutions for A, B, and C, and then we produced the explicit formula for the sum of consecutive squares. Okay? So our next project is going to be discovering the sum of consecutive cubes, sum of consecutive fourth powers. But I thank you all for your help. I thank Mr. Waterbury, our cameraman, and we thank our students here at Immaculate Conception.